What is going on, everybody? Welcome back to another video, Cup 1. Let's jump right into it. Here's another image that was sent to me by a listener or watcher, however the hell you want to, whatever sense you want to utilize. I thought this one actually really made me laugh. This is funny as hell. Control Z, if you understand Windows, Control Z, that's, go back. So I thought that was, really funny. So I wanted to show you really quick, whenever you close Jupyter Notebook, you can see my terminal is still running, even though I closed out of the browser. So if you go into your terminal and you hit Control C and C twice, so Control CC, it will kill the kernel. It'll shut it down. Awesome. And of course, Jupyter Notebook is constantly saving anytime you're doing any kind of work. So that's why you'll see all this saving. It's constantly doing that on a routine basis. You can see here it's every 2 minutes, but you can also hit the save button if you wanted to. So I'm going to close that out. We're going to open up another one because we're going to jump right back into Jupyter Notebooks and get hitting with our crash course of the second notebook. Come on, man. There we go. All right. So again, we have our terminal, Jupyter Notebook. Oh, I did caps and it still did it. What? All right, sweet. So crash course, that's where I want to go. And we already did the first one. I'm going to do the second notebook now. So today we're going to be talking about what's called the dot product. So in mathematics, dot, think of it as multiplication of two different elements together, but it's slightly varied. So again, and this is all in favor of NumPy. So we're going to shift enter, import NumPy as NP, shift enter, so that's loaded. And then you can see here we have two different variables, A equals np.array13 and B equals np.array24. So that's it, nothing special here. We're just creating two different NP arrays. And if I called AB, you know what? I will do it for you. Let's call AB. And it's just going to tell me array is 1, 3 and array, the second array is 2, 4. And now, of course, it doesn't give me this like it did in PyCharm where it would say what is A, what is B in terms of variable assignment if we were doing debugging, but we get it. We're not doing anything too crazy here. So here I have x1 equals np dot A comma B. So all we're doing is creating a new variable x1, and we're asking NumPy to do the dot method on the two arguments A and B, our two arrays that we've created from the variables, and then call x1. So we got 14. So if you don't know matrix multiplication, this is not going to make sense to you if you're looking at 1, 3, and 2, 4 and saying, how did you get to 14? So what I did was I quickly found, and this is something you're not seeing on here, but it's happening with the dot product, and I'm going to show you something called transpose. Is it on this or is it on the next one? Haha, transpose, there we go. All right, so that's actually very, very important. So something about matrix multiplication is you can't do them if the matrix are of the same exact dimensional size. So you can see here in this image, it says C equals AB with a capital T up here. And it says only if A and B have the same number of elements. And of course we have 2 and 2 in these elements, but the B, that capital T there, but the B means transpose B. So what that does is if A and B are like this, 1, 1, 3, 2, 4, like we have up top. And if you're looking, and I bring it like this so you can see everything in the same frame. So we have C equals A, so that for us it would be 1 comma 3, all right? A1 is 1, A2 would be 3. And then and ours is a 1 by 2. How many rows do we have? 1 row. How many columns? 2. So it's going to be a 1 by 2 matrix. And then, or array, the nomenclature is not going to be super crazy. But now look at B. B for us was 2 comma 4. B1 and B2 is going to be 2 and 4, but it's 2 comma 4. It's up and down though. It's vertical. So now it's not a 1 by 3. It's a 3 by 1. And that's what the transpose, that's what this capital T means. It's saying take this 2, 4 and make the rows into the new columns. So this would be 2 and then a 4 underneath it. And this will make more sense when we look at other examples later on. So B1 up here is 2, B2 is 4. And then what it's doing for mathematics, it's going to do A1 or 1 times B1. So A1, B1, that's going to be 1 times 2, and that's going to give us 2. And then we're going to have A2, which is 3 times 4, which is going to give us 12. And then we're adding 2 plus 12, and we're going to get 14. Now, one little quick trick, you can see this is a 1 by 3 and a 3 by 1. If you take the inner products of the matrix, so 3 and 3, they need to match in order to even be able to do matrix multiplication. not just in NumPy, but just matrix multiplication. The inners have to match. So 3 and 3 match, they're the same. So I can do matrix multiplication. And then the outer products, 1 and 1, is going to give me the dimensions of my final product, which is exactly this is. This is a 1 by 1. It's going to be a 1 row, 1 column, because we're getting a scalar, essentially. That's all we got was 14. And this is just showing you here, if we did the transpose of A times B, look immediately how you do not get the same results. Now, sometimes in mathematics, you know how you could say, 3 times 4 is the same as 4 times 3. You can do them either one, or 1/2 times 2 and 2 times 1/2. The order becomes irrelevant many times in mathematics. But with matrix multiplication, utilizing the dot product, that's what the matrix multiplication is, order absolutely matters, and again, it has to do with matrix sizing. So in this example, A is a 1 by 3. When you transpose it, you're going to get a 3 by 1, which we have here. And then if we kept B in its regular essence of just B, it's going to be a 1 by 3. What are our inner products? We have a 1 and a 1, and then our outer is 3 and 3. So look what you're going to get. You're going to get a 3 by 3 matrix if you do that multiplication. You can do it. Why can we do it? Because 1 and 1, the inner products match. So we can do it. Outer products are 3 and 3, so we're going to get a 3 by 3 matrix. So what this one's doing, if you follow this through here, it's doing A1 times B1, and then to get that first value, and then A1, B2, and then A1, B3, all to get that first row. And then it's going to do the second row, A2, B1, A2, B2, A2, B3 to get the second row, and then A3, B1, A3, B2, A3, B3 to get the third row. So depending on what you transpose, it absolutely does have, obviously, as you can see, a very different end product. So keep it in mind. Let's shift enter so we're through that. So I have here, when you transpose B, this would equate to 1 times 2 equals 2, 3 times 4 equals 12, 2, 12 is 14. That's exactly what we just did. And you could see. So now I just want to show you that if we can compare the speed, computational cost, and the resources. Obviously, you always want to have a faster computational speed anytime you're running code. So you don't have to, when we start getting into further machine learning projects, I'm going to have chunks of code that you're not going to know what they are yet, and you don't need to know what they are yet, but they're necessary to run. But it's not necessary to learn exactly what's going on at the moment. This is kind of like one of those, but I'm still going to run through this. So even though we already have NumPy imported at the top here, I am going to do it again for good measure. So import NumPy as NP, from datetime import datetime as DT. This is how, obviously, we're importing a library that has elements, that has library recalls for date and time. So A is np.random.rand end, and I'm putting in a value of 100. So I want to get random digits. B equals the same thing, randomly pick 100, and the time here I have is t is total 100,000. So I'm creating a function. I'm defining slow dot product. So A comma B, result equals 0, because it's like starting a counter at 0. For E, for every element, and F in zip AB. So it's every element. That's going to be for E, and then that's going to be F for B. Result equals result plus E times F. Return the result. So we're just calculating how long this dot product is going to be using a for loop. So we're doing the same thing that this did here, all of this, but we're doing it with a for loop. And then we're doing the, we're calculating the time for that to happen for the dot product. And then you can see we're having a slow dot product of AB. And then down here, we're calling dt.now. This is just making for the variable t0 calling dt, which was the library that we had, the datetime library up above. Obviously now is a function that's within that library saying the time right now that your computer has. And then we can subtract it by TO up top here at the end of it to find what is the now after it's done running minus when it started. So finish minus start is going to give us the time that the for loop happened in between. And here this A dot B is very similar, almost identical to what we did here in terms of running, because it has to do with certain syntax properties of Python we won't get into, but you could have done the same process here. It's running the same exact thing. So I'm going to run this, and again, you can go through this code, you can write this code if you so choose, but this is, I just wanted it to be explanatory, if you will. So here we go. It gave me dt1 over dt2 26.92. So what that's telling me is that the NumPy dot product ran 26 times faster than the for loop, the slow dot product for loop that we utilized here. And I'm going to run it again. So we got 26.9 kind of seeing how consistent. So 41 times faster. Each time I do it now, it's probably going to be in the 40s because we already used memory. So 39, 41. I keep going back and just hitting Shift Enter. 41. I'll do it one last time. And probably be 40. Yeah, 40.4. There you go. So 40 times faster to do the dot product than it is to do a for loop. Much faster is what I have here, and that's absolutely true. So just a quick lesson on some nomenclature. What is a matrix? Again, like I said before, a matrix is simply a rectangular array that's arranged in very specific rows and columns. People like to think of Microsoft Excel like a matrix, and it makes sense. Just understand that in the background coding process, under the hood, it's not, but it makes sense. Visually, it makes sense. So a matrix is a two-dimensional array, and it's read as rows, comma, columns. That's important because many times when we're indexing and we're trying to call particular portions of an array, we're going to index things as rows, comma, columns. So the first index is the row, second index is the column. And this is just showing an m by n matrix, m being the rows, n being the columns. And how many we go down here. So AI, comma, J is just AI is all the rows, comma, J is all of the columns. And then it's just showing you the location. This piece here is row 1, column 1, row 1, column 2, row 1, column 3, and so on. It is you can think of a matrix as a list of lists. So imagine this bracket was a Python list, and then we have this row would be another, this row would be a list. This row would be a list. This row would be a list. So you have a list of lists. That's all that means. And we can even use a list to initialize a matrix. Initialize in our world is it's initiating. It's to start something off. Oh, there we go. Anytime you hear initialize, you need to think to start. All right, good. I'm glad I put that in. So here, we have m equals an np.array, and you can see that we're calling the function array, so we have our quotations, and we're doing a list of lists, so that's why we have the double brackets. So we have our brackets to say we're having a list, and then inside that list, we're having two different rows. Row number 1 is 1, comma 2, which is column 1, row 1 in the column 2, and then same thing for the second row of 3, 4. Then we have a variable L, which is also a list of lists, but you'll notice this does not use the NP array. So I have here, they need to be the same size for now, meaning 2 elements and 2 elements. And then L is the same exact digits, right? Our same quote unquote matrix. The difference is L is a list of lists. M is a matrix, a NumPy matrix. So all I did here was, I will for good measure call L as well. So you can see that we got the M gave me the array, the NP array, and then the L gave me the Python list of lists. So now we're going to see what can we do differently with these two properties. So here for L, which is the Python list of lists, we're calling index 0. So I'm going to shift it so index 0, which again is always going to be the first position, and it pulls for me 1, comma 2. So that's awesome. So then I say, what if I want to get just the 1? What if I want to seclude the first aspect of it? Well, then I'd have to do first indexed list and then the first position or the first element in that index list. That's what this is going to be. So it gives me the number 1, and that's appropriate for L for the list of lists. Let's try the same thing on the NumPy array, and we get the same thing. So therefore that connotation works. If I just did M with the first index, it would have also given me 1, comma 2, because that is the first row in that particular matrix. Now I have M, and then you'll see here, I want to put this in the same screen so you can see this. This is our Python list. This is our NP array. I have 0, comma 0, and I pulled a 1. This cannot be done with a Python list, and that is true. And it pulled the 1 because it's saying in the first list in your matrix, the first row in your matrix, give me the first element. That's at 0, comma 0. And it gave me 1, which is appropriate. You cannot do that in Python. In the Python list, you're going to get an error. So if I wanted to call it in a Python list, I have to do index index. You cannot do 1 index with a comma. That's all that's showing. I want you to see that difference there with the comma. M1 equals np.matrix, open and close quotations. I'm sorry, parentheses, lose my mind. Open and close bracket for a list. Then we have our list of lists inside, which is going to be our matrix, which is a rectangular array. M1 is the official documentation where NumPy even says stay away from matrix function. So you see how we have np.matrix, we're using np.array. If I shift enter through this, it's going to give me a matrix 1, 2, 3, 4. It looks very similar to the array that we got when we printed M. 1, 2, 3, 4. What this just means here is that if you went and checked out NumPy's documentation for np.matrix, their own documentation says don't use this. So if you're ever doing another tutorial and or you're learning a new aspect and someone uses np.matrix, probably drop that resource, because even the NumPy's documentation says don't use this. It's there, but don't use it. And that's because of the back-end work that it would actually get you in trouble. But what you can do, if you ever did have to do that, I'm taking M2 here and I'm saying np.array M1. I'm taking the matrix that we just created here in M1 and I'm saying, you know what, man, give it to me in an array, because I can work with the array. And the NP documentation even says arrays are going to be much more user-friendly to us, and we can do a hell of a lot more to them. So all we did here was I took the matrix that we created, turns it into an array. M2.transpose. So here's what I was talking about before transpose when we got to the very beginning of this. It's the row of the original matrix becomes the column of the new matrix. So what does that mean? So I'm going to shift enter through there. So I just wanted you to see quick how it's row is 1, 2, and then next row is 3, 4. All it did was it took row 1. It said you're going to now, your first part element in the row, you're going to be the column. So then this 2 goes below it. And then it says, oh, you're the second row, you're 3, now you're going to become a column. And then it goes 3, 4 down. So 1, 2 down, 3, 4 down. So it transposed the matrix. So this I just have here, I copied this here from Google. Transpose the matrix of a new matrix where the rows and the columns are the original. So this is a great example to see. We have row 543, row 404, row 710, transposed. So I can already know the top, these are going to become the columns. So I go column 547, but then I keep the alignment. So under column 5, it's going to go 4, 3. So 5, 4, 3. This row is now going to go down, 404. This row is now going down, 710, 3. And that's all it's doing. And we have to do that many times because we have to match the matrix in order to do matrix multiplication. As you could see from, where are you? Up here, up top, we had to use the .t, the transpose. Here they have a superscript t, but in Python, and in NumPy rather, we use .t, which you can see here, capital T. It's important to say capital T. Superscript T, in their case superscript, but we're using a capital .t in the work that we do. That's how we do our transposing. So you can see again that we have a 4x2 matrix, and it's turning into a 2x4 matrix when it gets transposed. And so it still has the same elements, and the relationship of the elements is still standing. So this row 5, 4 is this, now we're going vertical 5, 4. 4, 0, the spatial element wise is still retained because now 4 zeros is going this way, 4 zeros. So 7, 10, 7, 10, negative 1, 8, negative 1, 8. So the spatial relationship still is maintained, and that's very important. And then I just have here a matrix is just a two-dimensional array. A matrix is a two-dimensional mathematical object containing numbers. And a vector is just a one-dimensional mathematical object containing arrays. So if you had a one-dimensional array, you can call it a vector if you want. Sometimes you just start to get a little crazy with connotation. So I have here, let's just make some general arrays to play with. Many times in some of the models that we're going to be doing, we just have to create an empty array, or an array that's just filled with zeros, or an array that's just filled with ones, or sometimes a diagonal. For whatever work we're doing. So here I just have z equals np.zeros, 10 comma d type equals integer. I wanted it to give me integer types only because I didn't want the decimal. I didn't want it to be a float, and the default is a float. 10 just means give me 10 zeros. So I created an array, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have an array of just zeros, 10 zeros. Very useful, in fact, which you will see later. Here I created p, a variable p equals np.zeros 10 by 10. So we have 10 rows, 10 columns, all of zeros. And again, data type was integer because I didn't want floats. If you kept this out, and if you got rid of this comma and you had quotation, parenthesis, then you would have gotten a 10 by 10, which would have been floats. It just looks messy, in my opinion. Then I have random matrix equals np.random.random, 10, 10. This random.random is going to give you a uniformly distributed numbers from 0 to 1. And you may want to use Gaussian distribution instead for the experiment, which we'll cover down here. That's the rand n. But I want to show you this, so let me shift enter. So this created a random.random matrix of 10 by 10s, but it's still a uniform distribution if you actually go through all of this. And this is actually very useful, even when we get to generative adversarial networks, GANs, we're utilizing in deep learning. So they are uniformly distributed zeros from 0 to 1, but some people you might prefer a Gaussian or normal distribution. Remember, we were talking about Gaussian one dimension, two dimension when we were talking about mathematical references. utilized in AI, ML, and DL. This has to do with standard deviations, and then how far out to the right and to the left is each grouping falling within that standard deviation. It's also known as the bell curve. But if you want to use this, you can. If you want your distribution of your array to be uniform above and below, then you use the rand_n function. What do I have here? All the arguments took in tuples, but the rand_n takes in each dimension as individual arguments, so pass each dimension separately. So here I have G, let me shift enter through it, equals np.random.rand 4 by 4. So 4 rows, 4 columns. We're putting in the dimensions of each piece. And you'll notice you're talking about, tuples, individual arguments, I don't get it. You see how this is open parenthesis, 4, comma 4, close parentheses? When we were calling before, we had to do double parentheses. We weren't just calling dimensionality, we were giving arguments. So here we're actually, it seems a small nuance, but it is different. But if you actually graphed this out, you would see that this is going to create a normal Gaussian distribution along the numbers that we called. And then based on that, we can also create the mean. If I wanted to call it g.mean, shift it out. So what it did was it took G, that was our random.rand_n array that we created. It said, give me the mean. So it calculated the mean based on this number. And if I wanted the variance, I could get g.var open close, and then I'm just calling the variance. So mean and var are simply just different methods that we're using to put on our NP arrays. And of course, this is all part of the mathematical operations that we're going to utilize. And many times when you're calling an algorithm, you might just put, we might have a library where we call, say, linear regression or logistical regression. And under the hood, it's doing all of this math. So you don't have to necessarily understand how to do all this per se, because you're not going to be writing it individually, but it's important to understand what the hell's going on under the hood. So I think that brings us to an end today for crash course number 2 for NumPy. Really good lesson on transpose of what a matrix is in terms of a rectangular array, and starting to understand rows and columns. Obviously, this is going to become monumentally important when we get to computer vision, and very important to understand. Not necessarily be able to do it, you should be able to do it though, but understand what all this means and how the hell transpose is aligning vectors so that it can do its vector matrix multiplication. All right, guys, to close out of a Jupyter Notebook, if you want to save any work you did, you could always hit save, and it tells you the last checkpoint that it was done. I'm going to hit log out up top here. It logged me out. I'm going to close there. I'm going to log out, bring down, and then of course we have our terminal. I'm going to control CC to kill that kernel. Rock on. All right, everyone, have an excellent day, and I will see you next time.